So we have finally come to the last section of this chapter on complex numbers, and this one involves quadratic equations. Although it's nothing new to us, but let's just for one last time go back to the definition of a quadratic equation. A quadratic equation is an equation that looks like this: ax squared plus bx plus c equals 0, where a, b and c are real numbers and a is not equal to 0. This condition ensures that we actually have a quadratic equation and not a linear equation. If a is equal to 0, then this reduces to the linear equation bx plus c equal to 0. And we also all know this well-known formula for the roots of this equation. This formula tells us that a quadratic equation has two roots and the roots are these. Now, there is no need for discussing this formula again. I will just simply draw your attention to this fact that the non-zeroness of a plays a role here because we are dividing by a. Alright. So although we know this formula, but we haven't really fully utilized the formula, in the sense that so far we have only used the formula in this case where b square minus 4ac is non-negative, is greater than or equal to 0. We know that this quantity is called the discriminant of the quadratic equation. It determines the nature of its roots. We also know that if this discriminant is positive, then the quadratic equation has two distinct real roots. If it is equal to 0, then both the roots are real and equal. But now we are going to consider the case where this is less than 0, it's negative. We have so far avoided this case because previously, when we did not know complex numbers, we did not really know how to make sense of square roots of negative real numbers. That is why we avoided this case. But now we can consider the case. And that's why let us assume that our discriminant is now negative. Then the formula is usual, just like before, same formula. But now in place of this square root, we can write root 4ac minus b square times I. Although you should be able to understand why this turns into this, but let me just show you one example that will make it clear. So you have a negative number under the square root sign, something like this. So by now you know very well that this actually equals square root of 5 times I. So that's how in place of minus 5 we have 5. So in place of b square minus 4ac we have 4ac minus b square times I, because that square root of minus 1 gets separated and gives us the imaginary unit. So now the roots are non-real complex numbers. Okay, so that's the thing. So let us now see some examples. Oh, and before the examples, we also have some notes, some comments. Let us first see them and then we will go to examples. Next, we have these two notes about quadratic equations in particular, but about polynomial equations in general. The first statement that you see here, it's a result actually from higher mathematics. It has a name also. It's called the fundamental theorem of algebra. It states that any polynomial equation whose coefficients are complex numbers, general complex numbers, has at least one complex root, which is a solution that is a complex number. Which means that the quadratic equations we are considering are a very special class of these polynomial equations, special for two reasons. The first is that they are polynomials of degree 2, whereas a general polynomial equation can have a polynomial of any degree, maybe 100 or 1000. And the second special thing is that the coefficients that we have in our equations are all real numbers. Real numbers are also complex numbers, but they are more special. And the second fact is this: a polynomial equation whose degree is n has exactly n complex roots, n solutions. One can use this fact and synthetic division, about which you know how to divide one polynomial by another, to prove this second fact. But you need not worry about these things, okay? So basically what it says is that a quadratic equation, because its degree is 2, will have two complex number roots, which we already know from that well-known formula. Those two roots may be equal, may not be equal, all those cases are there. Next, let us see the examples. So this is the first example. The equation here is x square plus 2 equals 0. If you were being asked to say something about the root of the equation, the nature of the root, then you have to separately calculate the discriminant. In this case, however, we have to just solve the equation. So without even thinking about whether the roots will be real or general complex numbers, you straight away just apply the formula for the roots. So in this case, A is 1, B is 0 because there is no x term, and C is 2. So accordingly, minus B, that means minus 0, plus or minus root B square, 0 square minus 4AC, 4 times 1 times 2, divided by 2A, 2 times 1. So this becomes plus or minus square root of minus 8 divided by 2. Square root of minus 1 is I, and square root of 8 is 2 times root 2. So if you do the calculation, you get this. Or you can do another thing, which in this case is easier than applying the formula. You can just solve the equation like how you usually solve such equations. You take the 2 on that side, it becomes minus 2, you take square root, so that way also you are going to get this. Let's see the next solution. So this is the next equation and its solution. The equation is x square plus x plus 1 equals 0. So in this case, A, B and C all are equal to 1. So the formula for the solution has been used: minus B plus or minus root B square minus 4 times A times C divided by 2 times A. So you can see that it will be 1 minus 4, so we have minus 3 under square root. So it will become root 3 times I. So these are the two non-real complex number solutions of this equation. So these solutions are in the system of complex numbers, but they are not real solutions. That means this equation is not solvable, does not have any root in the system of real numbers. And there is one more example. So we next have this example. Here the equation is root 5x square plus x plus root 5 equal to 0. So in this case, A and C are both equal to root 5 and B is 1, and accordingly these are the two solutions: minus B plus or minus root B square minus 4 times A times C divided by 2A. And if you do the calculation, this root 5 and root 5 will give you 5, 5 times 4 is 20. So you get minus 19. That means square root of 19 times I divided by 2 root 5. Now before I end this, the section ends here, and after that we will solve exercises, not today but in the next video. But before I end this, let us go back to those notes a little bit. The first statement in the notes was saying that any polynomial equation has at least one complex root where the coefficients are complex numbers. Say I write that down, okay, that equation. It will look something like this. an x to the power n plus a n minus 1 x to the power n minus 1 and so on plus a1 x plus a0 equal to 0. The expression that you see on the left hand side of this equation is a polynomial, because that's how polynomials are. Now here these coefficients in general are complex numbers, and I mentioned that there also in that first statement. They all belong to the set of all complex numbers, and we are saying that any such equation has at least one complex solution. Was it really necessary to mention that these AIs are complex numbers? So far we have defined polynomials only that are of this type, where the coefficients are complex numbers. Can they be something else? And the answer is yes. They can be objects other than complex numbers or real numbers also. But that is a topic of higher mathematics. If you are interested and if you get the chance of seeing those things, you will see how interesting they are. Where these objects are, in a sense, they are like numbers, but they are not exactly numbers. Okay, so I would just stop this small discussion here itself, and let's just end the video itself here. So in the next video on this, we will solve equations that are there in the exercises. And tomorrow, of course, we have our usual upload, whatever it is there. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.